All right, so in this video, we're going to look at finding the or estimating the error in an integral test example for an infinite series and also the alternating series test. These are the only two series tests that have error calculations for them. We saw that with the geometric series and the telescoping series, you can find exact values if the series converges. So you don't need errors in those cases. But in the integral test and the alternating series test, we have ways to estimate, sometimes crudely, but estimate the errors and therefore how many terms we need in order to actually get to that error or to get as close to that error as possible. So let's look at the integral test. The integral test basically has the remainder term going to be less than or equal to conservatively the integral from n to infinity of f of x dx, where f of x is the function that the series is based on. So, for instance, if our series is a sub n in terms of f of n, then we would use that explicit function for the sequence of terms as the function that we're integrating. Now, this is going to assume that we're actually calculating up the first capital N numbers of terms in that sequence, and then we want to know what the error is. So we're using the integral test to estimate this in the tail. Now, technically, there is potentially a bound on this remainder, that it's between this integral and n+1 to infinity of the same function. If you think about the way that the integral test works, that puts a sort of more precise bound on it. But generally, we're only looking for the maximum in most cases. And so this will do for our purposes, to only consider the upper bound on that remainder, not the lower bound on that remainder. Now, if you have a specific function, then of course you can actually calculate the error after so many terms. So let's say I want to find and estimate the sum from n equals 1 to infinity of 1 over n squared plus 1. And maybe I wanted to find out what the estimate was after 10 terms and then get the error on that. So find the estimate and the error after calculating the first 10 terms. So the first 10 terms I would physically calculate by plugging in the n equals 1, n equals 2, n equals 3, n equals 4, and physically adding that up. So the estimate would be 1 over 1 squared plus 1 plus 1 over 2 squared plus 1 plus 1 over 3 squared plus 1, etc., all the way up to 1 over 10 squared plus 1. So 1 over 2 plus 1 over 5 plus 1 over 10 plus 1 over 4 squared is 16, 17, plus 1 over 26 plus 1 over 37 plus 1 over 49 and 1 over 49, 50, 49 plus 1. 8 squared, 64 plus 1 would be 65. And then 8 squared, 9 squared, that would be 1 over 82. And then 1 over 101. So I would add that up, and that would be my estimate. But then the error on that estimate is going to be essentially the tail of my series. It's going to be from 10 to infinity. It was no bigger than the integral from 10 to infinity of 1 over x squared plus 1. And so if I go ahead and I calculate that, then I can find the maximum error. So at least I know, however far I am, whatever value this turns out to be, I know approximately how far away I am from the true value. I won't get to the true value, but at least I know about how far away I am. So it's the result of the sum of all the other terms. So if we do this actual antiderivative, we're going to get arctan of x, and we're going to evaluate that from ten to infinity. And I'm, being a little less than careful here. Technically, this is a limit as b goes to infinity of this result, but arctan, as it approaches infinity, is going to be pi over 2. And the second expression will be arctan of 10. Now remember, this is 10 radians. This is 10. Sort of how high is 10 and how close to pi over 2 does this turn out to be? Well, let's find out. You go to your calculator, and again, make sure that you're in radian mode, or this isn't going to work. Inverse tangent of 10, I end up with 1.4711276674. And if I subtract that from pi over 2, then I end up with 0.0996686, blah, blah, blah. So my error is within about 0.1, roughly, of the true value. So I could keep taking more values, and then I could keep calculating the error, and sort of approximating it along the way. Or I could try to determine, like, if I want an error of a particular value, then how many terms do I need to do that calculation? And so the way that would work, let's say I want my error to be, let's say 10 to the minus, let's say 10 to the minus 3. That's not a 3. There we go. So what I would do is I would essentially still have the same integral, but I would leave n in place and solve for it after the fact. So I would still have capital N to infinity of 1 over x squared plus 1 dx, and I would still end up with my arctan of x going from n to infinity, and that would still give me pi over 2 minus arctan n, and then I would set that to be approximately equal to 10 to the third, then to the negative third, or 0.001. And then what I would proceed to do from there is I would try to find the angle that would make this true. So I would have to do a little bit of a rearranging. So for instance, if I move my 0.001 over and then my arctan over, I would get pi divided by 2, pi divided by 2 minus 0.001 would have to be equal to arctan of n. And then I could say that tangent of pi over 2 minus 0.001 would give me n. So let's find out. Pi divided by 2 minus 0.001, and then take the tangent of that answer, and I did the inverse tangent. That was the wrong thing to do. 1.56, well, let's just retype it to make sure it's correct. Minus 0.001, the tangent of that difference. And I get approximately 999.9996667. And you always want to think of these counts as thresholds. So you need to round up. So this will be equal to 1,000. So if I wanted to get within 3 decimal places of my exact value for this sum, then I would need 1,000 terms to make that happen. That's a lot of terms. Now, the alternating series test is actually even simpler because you don't need any integration or anything. The error on the alternating series is just the next term. So the remainder after n is going to be less than or equal to the absolute value of a sub n plus 1. So let's consider an alternating series. So let's say I want to estimate, and again, assuming that it converges. So let's say I want to estimate n equals 1 to infinity of -1 to the n of n over 2 to the n. So I know that this is going to converge. I know this is going to converge because number one, it's alternating. And if I take the limit of n over 2 to the n, this does in fact go to 0. I can use L'Hopital's rule to prove that the limit does in fact go to 0. I could use the ratio test, for instance, to prove that also, that this does in fact converge. So now that I know that it converges, let's say I want to find the error. What is the error after adding up the first 10 terms? Well, the maximum possible error, and it's not, again, the exact error, but the maximum possible error is going to be the 11th term, the absolute value of it. The maximum possible error is the absolute value of the 11th term. So that would be, and again, I can ignore the -1 to the n because I'm taking the absolute value. It's going to be 11 over 2 to the 11th. Oops. I want the absolute value. There we go. Which is going to be approximately, I just throw it in the calculator. 2 to the 11th is about 2,000 and change. So 0.2 0.00537 ... So it's pretty small already. We're getting very close. The 2 to the n is going to really dominate this series. So, okay, well, what if I wanted to do a little bit better than this? What if I want the error to be as small as 10 to the negative fifth? How many terms do I need? Well, in that case, you're going to take your, again, the absolute value. So I'm going to ignore the negative 1 to the n. I'm going to set my n over 2 to the n to be, again, approximately equal to 10 to the negative fifth. Well, I have n's on both. I have a linear term and an exponential term. Really, the only way to do this is numerically or graphically. And I'm going to just throw it in my calculator. I'm going to put in my y and my ti, or you could do this on Desmos. X divided by 2 to the x. And then you can actually just go to your table, start someplace, integer values, put it on auto, and then just scroll down until you get your decimals far enough to 10 to the fifth. I got to somewhere around 21 or 22. If you plug in y1 of 22 or 21, let's see, 21 first is a little too high. And so I would have to put in n equals 22. N equals 22, because at n equals 21, I got 1.001 times 10 to the negative fifth. So it's a little too large. And so that intersection is, if this was a continuous function, is going to come at just above 21. And if you can't round down, right? So it's not quite small enough, not quite guaranteed to be small enough at the 21st term, but at the 22nd term, that will be 5 times 10 to the negative sixth. And so it will be smaller than this. So I would need n equals 22. So again, always round up to the next whole number. Again, because we're talking about a guaranteed number of terms to ensure that it's under this. This isn't, don't think of it as an estimate. Think of it as a threshold. So you can think of this as being technically strictly less than or equal to this error value. Now, sometimes you'll be able to solve this mechanically by algebraically, but with these combinations of polynomials and exponentials, there's really no way to do it except numerically. Now, this is the one thing to kind of keep in mind. This n equals 22 term is where the error is this small. So technically, this is n plus 1 and 2 to the n plus 1. So when I solve this n plus 1 to be 22, that 22nd term is the error term. And then the term where I stop counting is the nth term. So n equals, little n equals 22 is where the error is small enough to meet my requirements. Stop counting at the prior term. So in some ways, in some ways, this this alternating series is a little bit trickier because you're using exactly the same n value for both your integral and your the term you're stopping counting at. And so you don't have to worry about is this n or n plus 1. But in the alternating series, you stop counting at n, and the value of little n where you stop, where the error is smaller than that, is actually n plus 1. So the error is in the 22nd term, and then you stop counting at the prior term, so 21 terms.